So as we're looking at 2.4 day 1, when we are trying to find points of discontinuity, we're just talking about continuity in general. I think we should, step 1, what are your points of concern? Where might it be discontinuous? Step 2, for each point of concern, is it continuous there? And then step 3, at each point of discontinuity, what type of discontinuity is it? So first, for 131, if this is our function, I think our point of concern is x is equal to 0. That's where something bad might happen. So, is it continuous at x equals 0? Well, to be continuous, we need to show 1, f of 0 is defined. 2, the limit exists. 3, the limit and the function value agree at that point. But this fails, number 1, since f of 0 is undefined, so f is not continuous at 0. Turns out that I can show it is an infinite discontinuity, since if I take the limit from one side, this function explodes. So since this function explodes in a positive direction, that is an infinite discontinuity. I know that it's going to be always positive infinity because square root of x always gives me a positive, and 1 always gives me a positive. So for 131, if I look at this function, and let me make sure I say what the directions say. So for number 132, the directions say determine the points at which the function is discontinuous and classify those points. Okay, so when we look at this thing, if you're going to say where is it discontinuous, first thing I'm going to say is what are my points of concern? So I'm worried where the denominator might equal to 0. So I try and solve for those points, and I say x squared plus 1 equal to 0. Well, guess what? If you subtract 1, you get this. And where is x squared equal to negative 1? Well, those two graphs, y equals 1 and y equals x squared, never cross each other, so there's no solution. That means there are no points of concern, so it's continuous everywhere. And we can really see that when we look at what our graph looks like in Desmos. This thing, when you plug in 0, we get 2 over 1, which is 2. And the bottom's just never going to be 0 because I have a positive thing plus 1. This would have to be negative to make it 0 on the bottom, and it's just never going to happen. 133. Okay, I've got this function. So is it continuous? Well, what are my points of concern first? I think my points of concern are going to be where the denominator is equal to 0. So in this case, if I factor it, I get x times x minus 1. So I think x minus 1 with my denominator tells me that either 0 or 1 are my 2 points of concern. So is it continuous at x equals 0? Well, at x equals 0, we need to show, so for it to be continuous at 0, we need to show that the function value exists. We need to show that f of 0 exists. I need to show that the limit as x goes to 0 by function exists. Actually, instead of exists, I would probably say that this first thing is defined. And then for 3, I need to show the limit equals the function value. And so I'm going to now check, but I check number 1, and I notice that f of 0 is equal to 0 over 0, which is undefined, and so it fails the first condition. And And so we see that f is not continuous, or I should say f is discontinuous. F is discontinuous at x equals 0. Right. Okay. So it's discontinuous at x equals 0. So what kind of a problem is it? Well, notice, let me put that back up here. What discontinuity is it? Well, since the limit, so we've already shown that the function is undefined at that point. Since f of 0 undefined, and the limit as x goes to 0 of my function, x over x squared minus x, is equal to the limit as x goes to 0 of x over x, x minus 1. But that is just this times 1 over x minus 1 is equal to, what do I get? 1 over x minus 1. When you plug in 0, you get -1. Since f of 0 is undefined and the limit exists, that's trying to tell you, let me take all this and cut. That's trying to tell you that there's a hole. So since this happens and this happens, we have a hole, removable discontinuity at x is equal to 0. Right? Okay, that's where the removable discontinuity is. And then I'm going to add a page after this. And so at, what was it? X is equal to 1. X is equal to 1. Is it continuous? Because that was one of my points of concern. I had 2 points of concern, this one and this one. So first, we said, is it continuous at x is equal to 1, right? I'm sorry, x is equal to 0. And we said no, it was discontinuous, and it has a hole. But is it continuous at 1? Well, we would need to show, number 1, that f of 1 is defined. The limit as x goes to 1 of f of x exists, and that the limit is and the function value are the same thing. And so now I'm going to check. So look at number 1. When you plug in 1, do you get something out? No. When you plug in 1, f of 1 is just 1 over 1 times 1 minus 1. It's 1 over 0, which is a constant over 0, which is undefined. That means it fails. So f of x is discontinuous at x is equal to 1. But notice, this is telling us that we either have infinity or negative infinity. So the type of discontinuity, we're now thinking that it's probably a infinite discontinuity. And we can see that if we looked at the original, this is telling you have a hole at 0, and this is telling you you have a vertical asymptote. And so if we take the limit as x goes towards 1 from the left of x over x, x minus 1, what's something to the left? I'm going to test at x is equal to what? 0.9. And as you come in from the left, you're going to get a positive over a positive times a negative, which is positive over negative, which is going to give you negative infinity. And so this is an infinite discontinuity. So infinite discontinuity at x is equal to 1. We showed that it failed part of the definition of continuity. In this case, it failed the first one. We don't have to even check the other ones. And then for the type of discontinuity, we said that it turned out to be an infinite discontinuity. Now let's look at this one. It is a little weird, and oh yeah, let me go back here and hit paste. So here's a picture of the one that we just worked on. It's got this infinite discontinuity here at x is equal to 1, a vertical asymptote, and here's its hole at 0. So now for this function, if it's t to the negative 1 plus 1, that is 1 over t plus 1. But I think it's easier to see if we use a well-chosen 1 and write it as one term. So it's this over t. That's really the function that we're looking at. I think it's clear now that our point of concern is going to be t equals 0. And so what do I have to do to show if it's continuous there or not? I have to check 3 things. So we need to show, number 1, that g at 0 is defined. We need to show that the limit as t goes to 0 of g of t exists. And then number 3, the limit as t goes to 0 of g of t is the same as g of 0, and they match up. So I'm now going to come up here. Let me move this down. And maybe I move it all up here. All right. Now I'm going to check. Number 1. So I plug in 0. I say, look, g of 0 is 1 plus 0 over 0. So I get 1 over 0, which is a constant over 0. So that tells me my function's really wanting to be negative infinity or infinity as we approach that point, is what it's hinting at. So most importantly, this means that the function's undefined at the point, so it fails to be continuous. So we fail the first condition. So g of t is discontinuous at t is equal to 0. Now we have to see what kind it is. So what kind of discontinuity is it? Well, we know it's either negative infinity or infinity, so I'm going to test near 0. And so I'm going to say since the limit as t goes to 0 from, this time I'll go from the right of my function, I'm going to test at x is equal to 0.01. If I plug that in, I'm going to get a positive on top because 1 plus 0.01 is positive. On the bottom, it's going to be positive. So you're going to end up getting positive infinity for what our limit is. And that tells us that g of t has an infinite discontinuity at x is equal to what? 0. By definition, what it means to have an infinite discontinuity is that if it blows up as we come towards one side. All right, here we go. So now I look at this function, 5 over e to the x plus 2. Well, actually, let me go back here, and just to make sure we've got this, this is what our function ended up looking like here. And notice we definitely have a vertical asymptote at t is equal to 0. Okay, cool. All right, so if this is our function, 5 over e to the x plus 2, what we're worried about, point of concern, I worry about where the denominator is equal to 0. In this case, that would be where is this equal to 0. In other words, where is e to the x equal to negative 2? Well, I have memorized that e to the x looks like this, and it never crosses the x-axis. And then y is equal to -2 looks like this. So I do not think these will ever intersect. So this has no solution, which means that the denominator will be 0, never. Okay? So there are no points of concern. So this would be none. So f of x is continuous everywhere. And how would you see that? Well, let's go back to Desmos. E to the x plus 2. So it's 5 over e to the x plus 2. Let's see how pretty this looks. It's 5 divided by e to the x plus 2. It looks like that. What a pretty picture. So I grab that picture. It looks like as we go to the left, the function wants to be like what? 2 and a little bit. Maybe let's go to -infinity. I think it's wanting to go to 5 over 2. As it goes out to infinity, it wants to go to 0. We'll talk more about that in a future lesson. But the main thing now is to notice, that it doesn't have any points of discontinuity. So there's our function. That is 5 over e to the x plus 2 is equal to this right here. And you don't have to worry about what kind of discontinuity. Great work. This function 136. So where's an area or a point of concern? I think it would be x is equal to 2. Is it continuous there? Well, let's call this f of x. I don't know what they called it in the book. So I need to show that f of 2 is defined. You show that the limit as x goes to 2 of f exists. I need to show that the limit and the function are equal. So what the function is and what the function wants to be are equal to each other. So we need to show this. Let's come over here and check. Right. Take all of this, move it down. So what we get is we do the first one and do f of 2. You end up getting 0 over 0, which is undefined. We know that it's probably a whole, right? Look, we think it's a whole, right? Whole question mark. We don't know, right? So let's see. I'll put a question mark here. So what could it be? Well, the main thing we know is undefined, so it fails to be continuous there. So it fails the first condition. So f of x is discontinuous at x is equal to 2. And then you ask yourself, what type of discontinuity? Well, all we know so far is that since f of 2 is undefined, and, well, then we have to find out what happens for the limit. So we take the limit as x goes to 2 from the left, and the limit as x goes to 2 from the right. And guess what? This thing is really just absolute x over x translated to the right. So, looks like one of these, except that this point is now at x is equal to 2. So the limit as x goes to 2 from the left of f of x is going to be -1. As it comes in from the right, it's going to be 1. So this means we have a jump discontinuity, because both of the limits exist and they do not agree, because the limits exist but don't agree. That's why we have a jump. Awesome. 139. Okay, so for 139, our function What it says for this one is, for 139, it says that we check out the function f of x is equal to 2x squared minus 5x plus 3 over x minus 1. And then gives the hint at x equals 1. And then for 141 in a second, it's going to be g of u is equal to, 6u squared plus u minus 2, 2u minus 1, and it's 7/2. This is if u is not equal to a half, and this is if u is equal to a half. And here they want to know at u is equal to a half. Okay. So for 139, so I think they want us to check at x is equal to 1. And I was worried about it anyway because of this denominator. So I'm hoping that the top can factor. And if it can factor, I would have to have an x minus 1, right? When you put in 1, I think you're going to get a whole. So yes, x minus 1. And so would this be 2x, minus 3? So let's see. Let me make sure that's 2x minus 5x plus 3. So minus gets me plus. This gets me not quite what I wanted. 2x squared. Yeah, that's right. No, that gives me what I wanted. Minus 3 and minus 2 gives me minus 5. So there you go. So I factored it into this. So what we really have is we have this times this. So now I can really see what's going on with this function. I have a line that someone has busted a hole in, because this really only gives me a problem when x is equal to 1. So notice how math and science is all about form. I've rewritten it in this final form where I can really see it's just a line with a hole in it. So my point of concern was x is equal to 1. Is it continuous there? Well, I see that we need to show, and 1, 2, 3, I would have to have shown that f of 1 is defined. The limit as x goes to 1 of f of x exists, and that the limit as x goes to 1 is equal to f of 1. But it turns out that it fails this one, because when I check, I think you're going to see that f of 1 just ends up giving you 0 over 0, which is undefined, right? And then what kind of discontinuity is it? I think what you can see is since the limit as x goes to 0, the limit as x goes to 1 of this thing of my function is just this, right? Is the same as the limit as x goes to 1. Well, I can let this go away. And now when you plug in 1, you get negative 1. So that means the limit exists, and f of 1 is undefined. So we have a removable discontinuity, also known as a hole. All right, so 141, if we look at this thing, I think my only point of concern is here because it's something everywhere except a half. So really all I worry about is that they join up, right? So is it continuous? Well, we need to show a few things. Number one, at a half, I would need to show that g of a half is defined. I would need to show that the limit as x goes to a half of g of u exists. And I would have to show that the limit as x goes to Limit as x goes to what? 1/2 of g of u is equal to g of 1/2. So let's see. Well, I'm going to check. I see that g of 1/2 is just equal to 7/2 because they told me. And then the limit as x goes to 1/2 of 6u squared plus u minus 2 over 2u minus 1. If this limit is going to exist, there better be a factor on top. It shouldn't be x, excuse me, that should be u every time. There is no x. So if this is going to work out nicely at 1/2, then I better have a 2u minus 1 on top so that it can be a whole if it's going to have any chance of being continuous, right? But if I take a 2u minus 1 out of this one, well, I know that the first two have to multiply together to get the first. So I'm probably going to have 3u here. And the last two have to multiply together to get the last. So I'm probably going to have a plus 2 here. Is my guess correct? That gets me the right last term. This is -3 plus 4, gives me what I want, and that's it. So notice this limit exists because I can pull it out like we have. Over 2u minus 1. That equals 1. And if I can make this smaller and give myself some more room, resize, right, okay. That's just going to be the limit as x goes to 1/2 of, oh no, this one's not here anymore because it's over 1, right? Over 1, and so you get 3u plus 2. When you put in a half, that's 3/2 plus 2, right? But 2 is the same as 4/2. So it turns out to be 7/2. Well, look at that. So then we say 3. Notice that the limit as x goes to 2 of 1, I'm sorry, x goes to 1/2 of gu is equal to g of 1/2, because we just showed it, right? We just showed that this is equal to this limit. Thus, g of u is continuous at x is equal to 1/2. Yay! Okay, then 143. Is this the last one? Almost. 143, 145, 147. What was 143? 143 is f of x is equal to x squared minus e to the x minus 1. It's this if x is less than 0. It's this if x is greater than or equal to 0. And they want to check at x is equal to 0. So if this is my function, again, my point of concern is going to be x equals 0 because I worry if they join up. So if it's going to be continuous, we need to show f of 0 is defined. The limit as x goes to 0 of f exists. And then what the function wants to be and what it is are actually equal. So that's the 1, 2, 3 things that we need to check. So I go up here and I check. Well, first, f of 0 is equal to, put it in the bottom piece because it's equal. 0 minus 1 is -1. So that's okay. I can get something out. The limit as x goes to 0, well, to figure that out, I'm going to have to go from the left. I'm going to have to go from the right, and they better be equal. So if I come from the left, this is just equal to, left, I'm going to use the top piece, because that's where x is less than 0. x squared minus e to the x. So when you plug in 0 into this, you get 0 squared minus e to the 0, which is 0 minus 1, which is negative 1. As you come in from the right, it's this piece. So when you put in 0, you get negative 1. So this means that the overall limit exists and equals negative 1. But then 3 says that the limit as x goes to 0 is actually equal to f of 0. So f is continuous at x is equal to 0. Yay for us. 145. Okay, 145 and 147 are cute. It's saying, what value of k would I need to make this thing continuous? Right? Interesting. So I've got the limit as x goes to k. Well, notice I would need to come from the left. So it really looks like the only point I'm worried about. So it looks like my point of concern, where things might not be continuous, is x is equal to k. So we need to show that I can get something out, which I can. We need to show, is it clear that we need to show that k is defined? And that's going to be fine because you just plug in k. But really what we need is we need that limit to exist. So here's what we're going to do. We're going to say that the limit from the left is going to be something. The limit from the right is going to be something. We need them to agree. We're going to force them to work. So the limit from the left would use this piece. And the limit from the right is going to use this piece, right? And we need to force them to be equal. Well, if we come in from the left, this is going to give us 3k plus 2. If I put in k, this is going to be 2k minus 3. And we need, so force equality. I need to force them to be equal. So if I force them to be equal, then this would have to be equal to this, which means k would have to be equal to negative 5. So if k is equal to negative 5, then these two would agree. 15. And the limit would exist. And then what we have to check is, let's see, resize. So this would be, so if k is equal to negative 5, that means the limit as x goes to negative 5 of f of x would exist because they would be equal. And what would they be? Exist, and it would equal, well, I could plug in a negative 5 into either. So how about 3 negative 5 plus 2? That's negative 15 plus 2, or negative 13. So the limit would exist, and it would equal 13. So now all I have to show, that's actually number 2 of continuity. Number 1, if I did f of negative 5, I'd put it into the bottom one, and I get 2 times negative 5 minus 3 is negative 13. So the function exists, the limit exists, and number 3, yes, they're equal. So that would force it, force f of x to be continuous. F is continuous at x is equal to negative 5. So the choice that you want is k is equal to negative 5. Okay, here this is cute because now what do I need to happen? The way to think about this one, again, I needed to satisfy my conditions of continuity. So for this one, I needed them to join up. But I think the same thing, I need them to join up here. So I want this to be continuous at -2. So we need to show first that f of -2 is defined. So what is f of -2? And then we're going to show that the limit as x goes to -2 exists. And then 1, 2, 3, we're going to show that the limit as x goes to -2 is equal to f of -2, right? So let's check. First, for 1, f of -2 is just equal to k. So we get something out as long as I can pick my k, which I can because I'm going to pick it. So that's okay. Pun intended. So 2, I need to show that the limit exists. So I take the limit as x goes to -2 of this thing. Can I take a limit? Let's see. What do I hope happens? Well, I hope that there's an x plus 2 on top so that I can cancel it out and make a hole. And then I'm going to use that k value to fill in the hole. Do you see that? So if I factor out the top, I think it's going to be this. You can double check me and make sure I'm right. But then what that gives you is x plus 2 over x plus 2 times x plus 1. So that's just equal to 1. That's where our hole is, right? So this limit is equal to this limit without the hole. So these are not the same functions. This one has a hole and this one doesn't, but their limits are equal at -2, and you end up getting what? You end up getting -1. So my limit exists and is -1. The function can be equal to whatever I say it is. So I am continuous if I set k equal to -1 gives continuity. Because if k is equal to 1, that's going to be what my function value would be here. And that's going to be equal to my limit. And step 3 just says if the function value and the limit agree, then it's continuous to the point, and that's what we need. So that was 147, the last one of today. Have a great day. Peace out, Girl Scout. And I will stop.